It is a pleasure. It is a pleasure today to host Vasily Belokurov for our seminar in the Institute of Astrophysics. Let me present him briefly for those of you who don't yet know him, although there must be very few that don't really know him. Vasily was born in the former Soviet Union, and then he moved in England for his PhD. He did his PhD in the University of Oxford in 2003 on variability surveys in astronomy. And then he made his first postdoc in the Institute of Astronomy in Cambridge. And he liked the place so much that he decided to stay there forever, first in a Royal Society fellowship and later as staff member. And his current position is a professor of astronomy in Cambridge. His main interests concern galactic structure and dynamics, but also gravitational lensing, large-scale surveys like SDSS or Gaia. In particular, he is one of the most active participants in this revolution, which was brought in our understanding of the Milky Way by the Gaia satellite. A real revolution in which he contributed a lot with his pioneer work on the structure and substructure of the galactic halo, the discovery and modeling of stellar streams in the Milky Way, like the famous Sagittarius stream, the discovery and modeling of the local group, the galactic ultra-faint dwarf galaxies, and last but not least, the discovery and modeling of the ancient galactic major merger, which took place about 10 billion years ago, the so-called Gaia and Enceladus sausage. Has different names depending on who discovered that and in which conditions. And today he's going to tell us more about this last particular point, which is one of the hot topics in the physics of the Milky Way today. So Vasily, the floor is yours.
Thank you, Nikos. Thank you guys for joining us. Let's kick off. Do you see my screen?
Yes.
Perfect. Lovely. Okay, so the transformation of the Milky Way is the topic today. Nikos already alluded that it's going to be about this particular significant merger between our galaxy, a collision between our galaxy and a dwarf galaxy. So I'll go one step back just to give you a bird's eye view, which may help to set the scene. So a simple question: when did the Milky Way become the galaxy that we know, that we see around us now? And the good guess is that it probably happened quite a long time ago. And the reason for this can be already gleaned from these couple of plots, right? On the left, you see the famous Maddow and Dickinson compilation of star formation rates across a wide range of redshifts. And to understand this, on the right, you see the merger rate as a function of redshift. And you can see that most of the activity when galaxies form, merge with other galaxies, restructure themselves, happen at redshift up to 2, right? And from redshift 2, this activity subsided. And you can explain this by looking at n-body simulation of structure formation with dark matter only, at how many mergers you have as a function of redshift for halos of different mass. And you can see that typically the number of mergers is constantly decreasing from high redshift to redshift 0, but it was decreasing at lower, slower rate up to redshift 2, from where it started to drop precipitously. So most of the mergers happened around redshift 2 or before. So that's where we expect the most important events in the life of the Milky Way to happen. So what can these mergers do to a young forming galaxy? Well, actually quite a lot. And here I'm listing a few things, a few transformational events in the life of a galaxy that can be brought about by mergers, right? So mergers with smaller dwarf galaxies can nonetheless destroy, puff up the disk, a proto-disk of a Milky Way-like galaxy. Mergers and interactions can in fact flip and swing the disk altogether. You can induce bar seeding and bar buckling, so bar formation and subsequent bar buckling. You can seed spiral arms. You can suppress star formation in the galaxy, but you can also promote it. So actually, a lot of transformations can be spawned by interaction with a massive perturber. So what happened in the Milky Way actually depends on the history of the Milky Way, right? So we need to understand what and when merged with our galaxy. So we need to understand the masses of the emergent dwarfs. We would also like to know their gas fractions. And of course, to reconstruct the interactions, we need an idea of geometry and the kinematics. So how do we do this? Well, the answer is very simple, right? So there is information that is preserved forever in our galaxy, and it's preserved in the halo of the Milky Way. So here's a simulation built with Aquarius, one of the Aquarius zoom-in runs, where stars are painted onto the dwarf subhalos emerging with this host galaxy in here, and the color represent a single progenitor subhalo, right? And you can see that after a while, there is a giant mass forming in the middle of this dark matter halo, which represents the Milky Way galaxy. However, if you look, instead of the position space, which is shown to you here in projection in this animation, if you look instead in the space of integrals of motion, you can see that individual accretion events can actually be detected and recovered quite easily if you have access to, say, a projection of angular momentum and energy, or some other integrals of motion actions, for example, right? And that's because these interactions, even though they look dramatic, they are largely collisionless. And all this mixing and subsequent churning is really just the phase mixing in action growth with time of the difference of orbital phases. And so the integrals of motion are preserved, and if you can measure them, you can reconstruct the individual accretion events. So that's the idea. And we tried this, and we looked at the orbital properties of stars in the Milky Way since very early on, right? So this is one of the pioneering examples of connecting the chemistry and dynamics by Hagen, Lindenbell, and Sandage in 1962, right? So you have a metallicity, or poor man's metallicity, on the y-axis. It's UV which gives you an idea of the metallicity of the star, and eccentricity on the x-axis, right? And then similar plot now with real metallicities versus eccentricity by Chiba and Beers some 40 years later. And then, of course, in the subsequent 10 years, a decade of Sloan digital sky survey, and we have obtained much more accurate estimates of eccentricity and better measurements of metallicity for much larger samples of stars, right? And you can see that the pattern have evolved, these patterns in the space of metallicity and eccentricity have evolved. They look slightly different. Some correlations disappeared. For example, the correlation that was claimed by Hagen, Lindenbell, and Sandage. But overall, kind of the amount of grouping is more or less preserved. And every time we've looked at this space of chemodynamical properties of stars in the disk and in the halo around the solar neighborhood, we use different buzzwords to describe what we saw, right? So Hagen, Lindenbell, and Sandage invoked monolithic collapse to explain how a galaxy formed. Chiba and Beers, 40 years later, said, well, we see some clumping, we think it's evidence for mergers. And then later, 10 years later, Carolla and collaborators pointed out that perhaps our halo has dual structure. So we looked at the same plane, similar behavior of stars, and we interpreted very differently. And so here I'm giving you a talk where I'm going to interpret it yet again in a very different way, but I'm going to be looking more or less at the same plane, linking metallicity and orbital properties of stars. But before we made these discoveries, actually this discovery was predicted and hypothesized by Alice Deason, who looked a few years before Gaia was launched at the behavior of the stellar halo density profile and pointed out that in the Milky Way, there is a prominent, very significant break in the radial density of the halo stars, right? At a particular distance of between 20 and 30 kpc, the behavior of the density changes from shallowish to very steep. And so when Alice looked in the simulations, zoom-in simulations of formation of the Milky Way, the only way to produce such a break in the stellar halo density was by the stellar halo being dominated by a single massive accretion event that happened relatively early, right? And so then the break is essentially an apocentric pileup from the materials stripped from that dwarf galaxy. And that's why it can be prominent, because there was no other accretion event that would have its apocentric pileup at a different distance. And so you will have multiple breaks. When you have a superposition of multiple breaks, you will erase any one particular signature, right? So to keep one break alive, you need just one most important event in the life of the galaxy. And that also has to happen relatively early. So that was all before Gaia. Now we have Gaia. Can we test this idea of Alice Deason, and what can we gain from looking at this space of chemistry and orbital properties, this space that's been looked at many, many times before. So just a quick foray into what we did. We actually had a sneak peek at the Gaia DR2 data before Gaia DR2 data was released, not by hacking into the computers of the Gaia consortium, by actually taking Gaia DR1 data and improving, adding to it by combining it with Sloan Digital Sky Survey. So what Sergei Kopasov did was quite an impressive feat of genius. He took the Gaia data, Gaia DR1 that just had positions, and used it as a reference frame to re-derive the astrometric mapping between the CCD coordinates and on-sky coordinates for the entirety of the Sloan Digital Sky Survey, right? So he used Gaia DR1 to improve Sloan Digital Sky Survey astrometry, and you can see this improvement in the behavior of quasars. So on the left, these are motions of quasars before this recalibration of Sloan astrometry with Gaia. And then on the right, after, you can see that quasars moved a lot. So this Sloan's astrometric calibration was not so impressive and varied systematically across the sky. And it could be tied down by using huge number of reference stars that Gaia DR1 supplied. So when you look at the quality we would get with this combination of Gaia DR1 and Sloan Digital Sky Survey, that's here in the plane of proper motion uncertainty on the y-axis and the magnitude of the star on the x-axis. And you can see that essentially these red, orange, purpley curves is the prediction for the Gaia DR2 astrometric quality. And the stars from Gaia and Sloan are sitting at faintish magnitudes, and they're pretty much bang on the curve for the Gaia DR2. But we could look at these DR1 plus SDSS data a year or so before DR2 was released, and actually try to understand what's going on in the solar neighborhood, in particular in the halo. So here's a gallery of slices through the velocity space in the solar neighborhood. And you can just take it all in and maybe pay attention to how the structure of the velocity space varies left to right and doesn't change that much up and down. So what's plotted in each panel is radial velocity on the x-axis and azimuthal velocity aligned with rotation of the Milky Way on the y-axis. And the individual panels, as you go from left to right, are different metallicity slices. You start metal poor on the left, and you go more and more metal rich as you go to the right. And what you notice is that as you move from the left to the right, the structure of the density distribution in the velocity space is changing. You can see that it's more or less spherically symmetric on the left-hand side. And then it breaks into two components as you go to the right. A component at significant azimuthal velocity close to 200, which is basically a rotating population of stars. And then at the just below, let me just try to illustrate this with a marker, right? So this is a rotating population, right? So this is 200 velocity, V phi. And then there is another population sitting underneath in the shape of this sausage. And it's probably easiest seen here, right? It has zero or near zero azimuthal velocity, but it has gigantic velocity dispersion in the radial direction, right? And so as you go up and down in these plots, you're moving further away from the galactic plane, right? So that's why in this middle row, the rotating component is almost gone. And when you move further out, it's difficult to see at all, right? So you're moving away from the galactic plane, you're getting rid of your thick and thin disk contamination. But of course, as you move away, the quality of your astrometry decreases. So you can see that all the distribution in the bottom row are much broader, and they're broadened by errors, right? So you can see that the errors are growing, the errors are shown here. But what you can do, you can now model the distribution of velocities in this space and try to see if there are multiple components present. And indeed, there are components like the disk that I just showed you and the sausage-like distribution, which we attribute to halo. But you can also track their behavior with distance from the galactic plane and as a function of metallicity. So what we're doing is basically multiple Gaussian modeling of the velocity distribution as a function of metallicity and height from the galactic plane, right? And the most important thing that comes out of this modeling is that we see a clear dichotomy between kind of a mid-ball roundish shape for the metal poor stars and the sausage-like shape, very stretched in the radial direction for the metal rich stars. And then we see a sharp transition in the halo from this spherically symmetric to radially anisotropic sausage, right? And so just a quick refresh on how you can describe your velocity distribution. You can describe it with one parameter, so-called orbital anisotropy, which just combines the sizes of your velocity ellipsoid, the tangential motion, the amplitude of tangential motion in numerator, and scales it by the amplitude of radial motion in denominator. So this beta essentially is telling you the shape of the velocity ellipsoid, of course, under the assumption that it is Gaussian in nature, right? And so if you have isotropic velocity distribution, so beta is 0, radial anisotropy, beta will be positive, and you can stretch it to beta of 1 on completely radial orbits dominating. And then tangential anisotropy, you're going to be stretching your velocity ellipsoid in the other direction. And you can go to minus infinity if you increase tangential anisotropy for your group of stars. And so the nice thing about studying halo in velocity space we limited ourselves to a very small chunk of the galaxy around the solar neighborhood. But the behavior in velocity space, of course, by invoking continuity equations, you can link to the properties of the halo throughout the virial volume of the galaxy. So a small snapshot of velocities of stars near the sun actually tell you quite a lot about the properties of the halo of the overall. So what we saw in the halo as a function of metallicity and the distance from the galactic plane is summarized here in these 3 panels. So on the x-axis is metallicity in all 3 panels. And first left panel shows the velocity dispersion. And you can see that curves are split into different styles, right? So there are solid curves, dashed and dotted, and these are individual velocity dispersion, radial and the 2 tangential components. And different colors at different heights from the galactic plane. So red closest, green intermediate, blue is the furthest away. Because we modeled the velocity distribution, we can take errors into account. So this blurring that happened due to the astrometry getting progressively worse at larger distances is actually taken into account in this model. And you can see that the distance away from the galactic plane doesn't change much, right? So once you've taken care of your measurement errors, the behavior is actually consistent with each other. Most curves are consistent with each other. So the middle panel is perhaps most interesting, that shows the velocity anisotropy that I just described to you as a function of metallicity, right? And you can see that there's something particularly happen, right? At the low metallicity, you have nearly isotropic beta, close to 0, right? And that's consistent with multiple accretion events of small dwarfs coming from different directions with different impact parameters, mixing together, creating nearly isotropic halo, right? But at the high metallicity, you have this sudden jump, right? You have a completely different set of stars, right? And they have extremely radial behavior, right? So this beta is close to 1. And so all these stars in the metal-rich part of the halo are moving in the same way. They're moving in and out on nearly radial orbits. But the interesting thing is when you look at the numbers of stars, right? So they're shown in the top corners of this panel. Metal-poor stars are actually subdominant compared to metal-rich stars, right? There are 10 times more metal-rich stars than metal-poor stars in the halo. So what that means is that this strange radial motion is actually shared by the majority of halo stars. So we have the bulk of the halo doing the same thing, kind of constantly exploding and imploding back in, exploding and imploding back in, moving on this nearly radial orbit. So our interpretation is that this behavior is consistent with, indeed, with a single and rather massive, pretty ancient merger, right? And so the evidence for this comes from the change in the behavior of the shape of the velocity ellipsoid from this meatball into the sausage. And we notice that the sausage component actually is 2/3 of the local accreted halo, right? So the bulk of it is there. But you can go one step further. You can actually use metallicity luminosity relation for galaxies, right? It's shown in the bottom left corner here from a paper by Kirby and co-authors. And we know that this metallicity stellar luminosity relation is established in galaxies due to the gas outflows during the star formation episodes, right? So the low mass galaxies cannot self-enrich to values as high as their more massive counterparts can, right? So the energetics of the stellar winds and supernova explosions are universal, but the restoring force that you need to keep the gas from escaping so you can reuse it is increasing as you increase the mass of the host. So that establishes the relationship between the mean metallicity and the stellar luminosity of the galaxy. And so, of course, we can use the mean metallicity of the stars in this dominant halo component, right, and we know it's of order of minus 1.2, and we can just read off this plot immediately, roughly the stellar mass of the object that must have merged with the Milky Way. And it comes about 10 to the 8 or so, maybe more solar, right? So that's already pretty chunky, pretty large galaxy. So we can go yet another step forward, and we can compare the stellar halo properties as we measured it around the solar neighborhood to numerical counterparts of the Milky Way, right? So we can look at the cosmological zoom-ins and see what actually produces these highly radially anisotropic stellar halo components that permeate the halo of the galaxy well within, solar radius inwards and outwards, right? So the inner parts of the stellar halo. So you need to bring material into the deep down into the potential well of the galaxy. And so it turns out that you can only do it when you accrete massive dwarf galaxies. And so the bottom right plot shows you what objects create anisotropy that is shown on the y-axis as a function of redshift of accretion. And so the three curves here are three different mass bands for the satellites that are being accreted. So the most massive are red, then the least massive are blue, and the intermediate mass is green. So these are different mass progenitors, and they're accreted at different times, and the redshift is shown on the x-axis. And you can, once you've accreted these guys, right, so you can look at the debris distribution at redshift 0 and see what sort of orbital anisotropies you get. And you can see that high orbital anisotropies in the solar neighborhood are only produced by these massive objects. So these objects with masses in excess of 10 to the 10 solar. So that's now total mass. So on the left, I was talking about stellar mass, and this comparison with simulation tells you about the total dark matter mass. Just checking the time here. Okay, cool. So I've shown you this gallery of velocity distributions for solar neighborhood as a function of metallicity and galactic height. So now I've removed our model from the observed data, and what you're looking at now in the same kind of gallery are the residuals, right? And so you can see that in the metal-rich regime, where I just said where the sausage dominates, the residuals are particularly bad, right? So this is the part of this gallery where things are not so good, right? You can see that there are strong residuals on either side of the sausage distribution. Well, actually that happens because this velocity distribution is not Gaussian, right? So there is no reason to believe that it should be Gaussian in the case of one accretion event dominating the distribution of orbital properties. So these lobes at high radial velocity, negative and positives, are to do with the solar neighborhood crossing a chevron-like structure that is produced by this radial merger. And so here I'm just sending a test particle on a radial orbit in the Milky Way-like potential. And you can see that somewhere around 10 kiloparsec where the sun is, if you have a cross section of this distribution, you will see two bunches of stars at high negative velocities that are coming in and high positive radial velocities that are coming out, right? So stars are streaming in and streaming out. So that's why the velocity distribution is highly non-Gaussian. So here, slightly more interesting phase mixing exercise where I'm adding test particles kind of in a Gaussian packet that would be stripped or mimicking the stripping episode. in this accretion event. And so what ensues is just a phase mixing. And you can see that in position space, the phase mixing leads to redistribution of these particles. And in the velocity, in the phase space, the radial velocity versus distance, again, you are mapping out this chevron. And of course, if you now slice it, as shown by this blue band here around the solar neighborhood, you're gonna get in the velocity space, radial versus azimuthal shown in the bottom right panel. You're gonna get this sausage-like structure, right? And that's from all the particles zooming in and zooming out, but you're also going to get the two over densities on high negative and high positive on the sides of this chevron that you've created. So highly structured distribution in velocities because of the nature, this head-on collision, radial-like mergers. But you can also see in the top panels that some of the shape and the orientation is preserved after a long period of phase mixing, right? So the final kind of direction of the smash of the collision produces this elongated triaxial structure or bow tie, depending on which direction you're looking at it, right? And the shape and the orientation of that structure to do with the final bout of disruption is actually preserved after many giga-years of phase mixing. That's an interesting thing. So this was all kind of our exploration before DR2 came. And then with DR2, of course, you could do a lot more. And multiple groups and multiple papers produced beautiful new ways of studying the same event, right? So it was seen immediately, the glimpse of it was seen in just in the color magnitude diagram built with Gaia DR2 data. So this is a Hirschsprung-Russell diagram on the left, one of the science verifications papers by the Gaia team. And you can see that the main sequence turn-off for stars with high tangential motions is split in two, right? So stars with high tangential motions basically means stars on halo-like orbits. So see here, your halo is actually split in two more or less equal portions, right? The stars with blue turn-off and stars with red turn-off. And similarly, you can see two types of halo stars when you look in the velocity space, right? So you combine the tangential components and show them on the y-axis and the radial component on the x-axis. Sorry, this is the azimuthal component, just not to confuse you, right? So the stars rotating with the sun will be around 0. So stars not rotating with the sun will be at a negative rotation velocity around the solar neighborhood, right? So at minus 220, right? And you can see that stars around the blue turn off and stars at around red turn off in the left color magnitude diagram, they are both halo stars, but their distribution in the velocity space is already quite distinct. So the blue stars have higher amplitude of the motion in U plus W. So that's radial and vertical motions combined, while the red stars have actually components closer to the thick disk tail, right? So they have some contribution from the azimuthal rotational velocity, but also lots of stars with essentially 0 rotation or even retrograde. But already you can see two distinct halo components. And I'll explain why there are two halo components. One of them is predominantly this one merger event that I described, this sausage, and the other halo component is something else. So if there was a significant merger in the past of the Milky Way, there was a big dwarf galaxy that came in, we expect that that galaxy had an entourage of its own globular clusters. So immediately we looked in the the new freshly released Gaia data to see if there is a group of globular clusters that would stand out and will look to have similar properties, orbital properties, to what we think that merger, that progenitor galaxy had. And indeed, there are globular clusters that appear to be on highly radial orbits, right? And you can see that they're on highly radial orbits when you compare the pericenter, shown on the y-axis, with the apocenter. So all these globular clusters have extremely small pericenters and very large uppers. So that tells you already that they come in very close to the galactic center and then they fly out to large distances. So they all sit together in with very similar eccentricity. And there are at least 10 of them or so. And then, of course, you know, you can take the number of globular clusters and you can convert it to an estimate of the stellar mass of a dwarf galaxy, because we know there is a specific frequency of globular clusters that you can use to, that correlates with the stellar mass. So the number of globular clusters is already an independent confirmation of a mass of that progenitor system. We also checked directly the orbital properties with Gaia DR2 of the metal-rich stars and metal-poor stars. And so metal-rich stars are here, the orbits are shown as red curves in the left and the right, and the metal-poor stars are shown as blue curves. And there are two different samples of stars. So you can look at the local stars, and this is the link to our original investigation. We looking at the halo just limited to a few kiloparsecs from the sun, right? So it's a very small volume, right? And we're trying to study the structure that is, you know, orders of magnitude larger. But so here we're trying to make a step out, right? And so the local main sequence stars, you can see that even though they zoom by the sun, they actually go to rather large distances, you know, 10, 15, 20 kiloparsec, like this star shown in red here. But you can compare these stars now to stars that you detect at their current position at much larger distances from the sun, right? So you need a different tracer. You cannot use main sequence stars anymore. So you use stars that are more luminous, but still good standard candles. So we use blue horizontal bright stars. So these are stars burning helium. And so they can be used on as more or less a standard candle. So they are currently at a very different distance. But of course, with Gaia, you can now reconstruct their orbit. And you can see that the meteor-rich distant blue horizontal bright stars are actually doing the same thing as the nearby main sequence stars. They're also on this very highly eccentric, nearly radial orbit, moving in and out. So we're stepping out and we're seeing that this structure actually covers a very large portion of the inner galaxy. We believe probably it extends as far as the stellar halo break, which I said is at around 20, 30 kiloparsecs. And in fact, the debris from that merger is what creates this upper center pileup, as Alice Deason predicted and confirmed in 2018 as well. You can combine chemistry and dynamics very beautifully, and that's been done in a sequence of papers by Amina Helmi's group, by Ted Makarev, and Di Matteo's group, right? And these three papers looked at the chemical patterns. So they look at the alpha element abundances as a function of metallicity. And all these three panels show more or less the same, the alpha elements versus metallicity. And then you color code, or you track stars in the plane of alpha versus iron using orbital properties, right? And so you can use the velocity dispersion in the radial direction, or you can use eccentricity, or you can use energy. These quantities are all telling you more or less the same, how radial is your motion, right? So when you select stars that are on extremely eccentric, radially, almost nearly radial orbits, you see that they trace a particular pattern in the space of alpha versus iron, right? So this pattern I'll probably better annotate so I can show you, but you can and you stare at this, you'll see it already, right? So the pattern that I'm talking about is this characteristic drop known as alpha Ni that you can see in all these plots when you select stars of high eccentricity. And it's particularly clear in the Matteos plot, right? So there's this sequence. And this sequence is there because these stars come from the same galaxy. Only if they come from the same galaxy, they will show this coherent drop at a particular metallicity. And this drop in alpha element production happens because supernova of type 1a start to contribute after some time. There is a delay, right? So you can say that the type 2 supernova are instantaneous, right? The stars are born and then they explode because the delay time is extremely short. But type 1a supernova, because it's a different channel, you need to explode a white dwarf. There is a delay, right? And so the galaxy can self-enrich for a while, so its metallicity is increasing, right? So type 2 supernova are not very good by polluting the gas with heavy elements. And that's because the heaviest elements actually go into the dark remnants, right? Into neutron stars and black holes. So the pollution with heavy elements is not very efficient with type 2 supernova. But when you explode a white dwarf, you synthesize all the elements in the explosion and you put them all out into the interstellar medium. So when supernova type 1a start to contribute, the relative abundance of alpha elements start to decrease, right? And that happens in a particular moment in time in the life of the galaxy. And that's why you see a coherent drop, this Ni behavior. And this is because all the stars that are surrounding us, right? So we sit in the sea of these stars from that merger. But when you look at the chemistry or chemodynamic properties, you realize that they all come from the same object because they share orbital properties and they share very particular chemical enrichment history. So that's a very, very clear and very important clue about that particular event. So, of course, we wanted to see if these events are prevalent in cosmological simulations. So we looked at one particular suite of simulations, Auriga, and that's a project led by Rob Grant. There are 30 Milky Way numerical counterparts, and some of them are shown here. So we can do the same thing we've done with observations. We can decompose the velocity distributions locally around the sun into multiple components and tease out those Auriga halos that have the halos dominated by this sausage-like structure. And you can see on the left, this is the data from Gaia DR2 now. And on the right, different examples of velocity space. Again, x-axis radial, y-axis azimuthal for different Auriga hosts. And you can see that in some cases, you have a very clear sausage, but in many other cases, there is no such a strong radial anisotropic component locally around the sun. So there is a variety of outcomes in these simulations, and you can summarize the behavior of the host by measuring the anisotropy, the beta parameter for the prevalent halo component, and also estimate how much it contributes to the halo overall. So the fractional contribution is on the x-axis and the anisotropy is on the y-axis in this left panel. And the dashed corner basically carves out a region which we think is consistent with what we've measured for the Milky Way with Gaia data. And you can see that roughly a third of the Auriga hosts actually exhibit this behavior. And there are some that we've marked here in pink that are particularly strongly radially anisotropic and contribute the bulk of the stellar halos, so these guys. So when you select halos that show this sausage-like behavior, so strongly radially anisotropic velocity distribution around the sun in the halo, and go back and look at their mass assembly history, you notice they're shown here on the right-hand side, right? So this is cumulative mass assembly, right? So time is on the x-axis, and the mass in dark matter is on the y-axis. You can see, right, so now is on the right-hand side where it says 14, right? That's actually redshift 0. And so it's time from Big Bang. But you can see that when you select hosts that have this Gaia sausage-like structure in the halo, they all have gone through a particularly fast formation episode, right? So some 10 gigayears or so, their mass increased dramatically. So they all underwent a dramatic formation episode, an accretion that was punctuated by an accretion of this massive dwarf galaxy. But of course, there was more matter coming during that accretion episode. So that's an important thing to bear in mind. So by looking at the simulation, we can find out what was accreted, how long ago, and we do confirm that indeed 7 to 11 gigayears ago, something as big as the LMC merged, collided head-on with the Milky Way. So one thing is to talk about the stellar halo and make all these deductions from a very small volume around the sun. And another thing is actually map out this whole debris cloud throughout the virial volume of the galaxy. And to do so, we needed a completely different tracer. We needed a tracer that is luminous enough so we can see it at large distances, but also is a solid standard candle that we can measure distances precisely. And Gaia provided us with such stellar tracer, and this is the stars that we typically use to map stellar halo. The pulsating horizontal branch stars are Lyra. And it turns out that the bulk of their Lyra indeed is in this gigantic debris cloud that is left behind by this merger. So these are slices of their Lyra density in XY plane in galactocentric coordinates. And then you're also looking at XZ projection and YZ projection. And the nice thing here is that we also have a model of this distribution. So the blue contours are the data, but the orange dashed contours is our model of this distribution. So this distribution is clearly triaxial, and it's also misaligned with respect to the galactic plane. You can see that these contours kind of are not symmetric with respect to the galactic plane, which is this wide gap here. You can see that also the major axis has a particular direction that is actually aligned more or less with the so-called plane of satellites, or with, if you want, with the plane of the Magellanic family accretion, right? That's marked by this, the orange line here. That's the major axis, but it's more or less aligned with the plane of the Magellanic family accretion. But so how do we know that all these are Lyra that sit in this triaxial structure are part of that event? Well, that's actually betrayed by the kinematics. So even though for the Lyra, you don't get 3D velocity information because you don't get the line of sight velocity, you can actually map out the projection of the velocity ellipsoid on the sky, right? And so here I'm giving you a cartoon, a sketch of what a strongly radially stretched velocity ellipsoid would look like when you start projecting it on the plane of the galactic sky. So L and B is here, and these are different velocity ellipsoid as you scan through the sky. And you can see that when you have such a strong radial anisotropy, even when you look at the projection of the velocity ellipsoid, you can actually already tell more or less how stretched it is. And the second thing that we can use to our advantage is the fact that, as I said earlier on, that the distribution is actually not Gaussian at all. It has these two strong humps in the radial velocity to do with the stars zooming in, streaming in towards the galactic center and streaming out away from the galactic center in this chevron-like pattern. So you can use this to your advantage to reconstruct the behavior of stars, right? So here is a very striking, I think, plot that tells you immediately what's going on in the halo of the Milky Way. So there are three models shown: isotropic, tangentially isotropic, right? So you stretch in the velocity ellipsoid in the direction of tangential motion, and radially anisotropic model. And these three maps are showing you maps on the galactic sky. And I'm just showing you the correlation coefficient between the proper motion in longitudinal direction and latitudinal direction. And from this plot already, right, where I showed you the ellipsoids themselves, you can see that in radially anisotropic case, there is strong correlation between longitudinal and latitudinal direction. So stars are moving in kind of this diagonal fashion, right? So that's the bottom left model. And bottom right shows the data, and look at the very strong pattern of change in these correlation coefficient. So the coefficient that measures correlation of motion on the sky along L and along B. And this pattern of blue, red, copies completely the behavior of this radial anisotropic model, right? So, but what this data is showing is all the RLI within 30 kiloparsecs or so from the galactic center. This is their motion on the sky. So they all are participating in this highly radial motion. And that was, I think, one of the most striking confirmation of this debris, the existence of this debris cloud that was left by this event, but now not just in the solar neighborhood, but throughout the most of the volume of the galactic halo. Now I'm conscious of the time, and I don't want to overrun too much. So you can do even more sophisticated tricks to reconstruct the kinematics of these debris cloud. And so this was done most recently by Giuliano Iorio with some help from myself in last year, where we basically modeled the 5D properties of the RLI and map out this chevron structure in its entirety, kind of the separation of the peaks, the size of the chevron, how it decays. And that, of course, informs us of the geometry and the kinematics of the impact. Just in the last 2 minutes, I want to mention the response of the Milky Way. That, after all, that was the topic of the talk, right? So the Milky Way will not come out of this interaction unscuffed, right? So it will be transformed, and it will suffer, and it will change, right? And so the first very clear signature of the response of the Milky Way is, in fact, in these two halo sequences, the red and blue. And you can see that blue is highly energetic. It has stronger radial velocity amplitude. These blue stars are reaching higher velocities. And the red one, not as energetic, but still many stars on similar orbits. In fact, the first clues of this were already picked up by looking at the detailed chemistry of these stars, right? And so Deason and Schuster in 2010 noticed that halo stars present two sequences in this alpha iron plane, right? So the red and blue sequences. So here the color coding switched, unfortunately, right? So the red and blue on the left do not match red and blue on the right. So these two sequences I've already explained. One of them is the alpha sequence from the dwarf galaxy stars, right? And it starts to drop at around metallicity of minus 1.3, and it goes down in alpha elements. And then there is a sequence above it. And what it means, why the alpha elements are high while the galaxy manages to get to higher metallicity, is that this was fast star formation and self-pollution, right? So this was a bigger galaxy going through the motions, right? So bigger galaxies for a given amount of time can self-enrich to high values. And while they do this, the alpha elements stay high, right? Because this supernova type 1a haven't managed to kick in yet, right? So what we see in this upper sequence of alpha elements in blue symbols on the right, this is our stars, Milky Way stars. Only galaxy as big as the Milky Way can actually self-enrich to such high values, minus 0.4. So these stars were born in the Milky Way, but now are on halo orbits. We know that stars cannot be born in the halo. That's very difficult. There is no, the conditions there are not good for star formation. You need to have cold dense gas, and that cold dense gas only exists in the galactic plane, right? So these stars were somewhere close to the plane of the galaxies where they formed, and they were kicked out, splashed, as we called it, by this merger. And then there are multiple confirmations in the data for this splashing happening. And the important one important measurement that I'll probably finish with is the age distributions of the stars that are were born in the Milky Way and then were kicked out, right? So the age distribution of these stars is shown here as the black in the middle panel as the black curve. So this is just age, right? And so time 0 is now, and this is look back time, age, right? And so the black line shows you the distribution of ages of stars in the in situ component, born in the Milky Way, but on halo orbits now. And the blue histogram are the stars from this Gaia sausage dwarf galaxy. And you can see that the shapes are slightly different, but what they share in between each other, what's common for these two distributions, that they are truncated at around the same time. And that's because one is linked to the other. When the dwarf galaxy comes in, each star formation is suppressed, right? So it stops forming stars, and you can see the truncation around 10 gigayears. But what it does, it perturbs the disk of the protodisk of the young Milky Way, and it kicks out all the stars that were born before and during the interaction up on halo orbits. So you see the synchronicity of age distribution, of star formation histories of the dwarf galaxy and the Milky Way, because they're influencing each other. So you can use this, right? This is the final piece of the puzzle, what the galaxy did with the Milky Way to actually inform the epoch of this interaction, the energetics of this interaction, because the amount of stuff you kick up from the disk will depend on the mass ratio of the two objects, right? So this is the missing piece of the puzzle that you can use to reconstruct that interaction. So I'm almost done. I'm just going to put my conclusions. Right, so we have now a consensus with variety of measurements about the accretion time, right? So between 7 to 11 gigayears ago, we know something dramatic happened with the Milky Way, right? And we can actually estimate the mass of the perturber of the dwarf galaxy that came in and interacted with the Milky Way through a variety of different avenues, right? Globular clusters, metallicity-luminosity relationship, just structure of the debris cloud also tells us. We can measure the total mass of the stellar halo, and that gives us the upper limit. So we know that somewhere in the ballpark of few times 10 to the 8 solar masses, that was the stellar mass of that dwarf galaxy. And kind of the final important thing, that around the time when this massive dwarf galaxy came to interact with the Milky Way, we know that many things happen in the Milky Way. We always known about this, right? We've been looking at the Milky Way's properties, and we kept finding this particular epoch at around 8-9 gigayears ago, when our galaxy's disk transitioned from being thick to being thin, right? And I can unpack what it means separately. We also think that bar formation happened sometime around then, and also the bulge stars have ages typical of 8-9 gigayears. So you can see that many structural components of the Milky Way can be age dated back to exactly the same epoch when that particular event happened. And I'll finish with the list of not fully or not really answered questions, and there are many to do with the detailed chronology of interaction, to do with the mass and gas content of the dwarf, how the gas was used, what happened to its black holes. All these are the questions that we are hoping to answer now. So I stop here and thank you very much.
Okay, thank you very much, Vasily. Nikos, can you organize the questions, please?
Activate, yes. So Okay, thank you very much, Vasily, for this nice talk, which illustrates, among other things, the exquisite quality of the Gaia data. Without them, we would not have all these nice things now. So I see there are several people raising their hands, starting with Gary.
Okay, well, Nikos, you should add that about the exquisite quality of the people who analyzed the Gaia data, particularly in Cambridge.
Yeah, but this was obvious.
Thank you for kind words, guys.
Yeah, no, it's great stuff, Vasily. I'm very impressed. So I just have a basic question which I didn't understand, which is what do you think was the mass ratio of the two systems when they merged?
Yeah.
And how close did the dwarf get? Can you measure how close did the dwarf get? For example, what was the pericenter? The first pericenter in units of the scale lengths of the disk at the time of the major component.
Yeah. Okay. So you can get to the total masses of the dwarf and the host in a variety of ways. I'll do the simple one because it's the most direct. You use, say, abundance matching to go from stellar mass to dark matter mass. So, you know, at few times 10 to the 8, it will be 1 to 2 times 10 to the 11 total mass, right? So it is what we think roughly LMC's dark matter halo is. That's from our most recent measurements of that, right? So when you go back in Milky Way's history and again, look at what Milky Way's formation path was, we think the Milky Way was probably half of its current time then. So this means that you will arrive at the mass ratio that will be between, well, of order of 1 to 5, I would say. It could be maybe 1 to 3, maybe 1 to 7 in that ballpark. So the first pericenter is very interesting. The direction it's coming, the first pericenter distance, but it's much more difficult to constrain with the data that I've discussed with you now. There is very exciting new data set from the survey called H3. That's a kind of moderate, medium resolution spectroscopic survey of the halo of the Milky Way. I think Charlie Conroy is PI, and they have been starting to put out papers, and a couple of papers by Rohan Naidu actually discuss the implications for this merger. Why that data is interesting? Because they're mapping the halo at larger distances, so they have access to the information about the earlier, the beginning of the stripping. So they can use that data and try to interpret it to get an idea of the first pericenter. So I would refer you to Rohan Naidu's paper about the first pericenter. But what we can get from the data in hand is the position roughly of the final peri, right? And so that is shown here, right? So the at the bottom is this kind of chevron pattern that forms, and the peri is somewhere at 3-4 kpc here, where that's where the chevron is truncated, right? When the stars zoom by the peri, right, they reach their highest velocity and then they turn around. And so at the top is our reconstruction of it, right? So we fit in this 2-hump model in radial velocity to the RLIRA 5D data, and we reconstruct the half of the chevron. So what you see at the top is the reconstruction of the half of the chevron, but this is now observational. And so you can see that the turnover happens somewhere at around 5, and we see the structure continuing to 3-4 kpc. So that's where we think kind of the mean last peri is. Right, so that's the final phase of the disruption. But the first peri, of course, was further out. So I answered partly your question, and I'm happy to kind of direct you more to this Naidu's paper that came out, I think, a couple of weeks ago, and has like the first n-body reconstruction of what the event might have looked like, and it matches many of the observations that I described here. And one very beautiful thing is that it matches our map of this triaxial debris cloud structure that is kind of stuck at an angle through the disk. And in fact, what I haven't mentioned is that, you know, there are two largest overdensities in the halo that are known as Virgo overdensity, Earth plus Aquila, and they're also part of this debris cloud. Yeah, so there are many nice matches between their model and the data.
It'll be interesting also to find out whether the secondary was gas rich or not. It might have lost its gas by ram pressure before falling in, or maybe like the imaginary clouds will keep it. And that would, if it had gas, then it would create a burst of star formation within the primary stars.
Indeed.
And you showed in the end the nice plot with look back times or ages.
Yes.
And so I'm a little bit dumb on this. What was the third? The red component was high V phi. That's
Yes.
high V phi in absolute or relative to the sun. I didn't understand. So, it's probably an absolute. So that's the regular disk stars, right?
Yes. Yes. So the high V phi red is basically your thin disk, mostly thin disk, and you can see that it can start happening after the merge finished, and what you can see that indeed the star formation histories are aligned, right? And I think the satellite was gas rich, and it basically formed stars until last minute, right? Until it couldn't anymore. So some of it was stripped, but some of it, you know, not all the fuel was, you know, completely removed. And you can see that the splash population, these metal-rich in situ stars, it has some kind of interesting behavior at slightly later times that could be indicative of, you know, induced star formation. Mm-hmm. That there could be something happening indeed, like a star formation burst. What I haven't shown is this similar plots, but comparing to what happens in Auriga galaxies. I think this is very busy. The three rows are the same, so you can choose any of these rows. And so the star formation is shown in the top, sorry, in the right column, right? And the curves are the same. So you can see that sometimes there is indeed a burst in the in situ population around the time of accretion. These bursts are not huge, but they do happen.
Okay, great.
Okay.
Thank you.
So, thanks, Gary. So, next question, Norma Sanchez, please. Norma, try to keep it short as a question.
Yes, thank you very much, Nico and Vasily, for this presentation. I have no doubt, I mean, exquisite analysis, data and analysis of these results. My question is, why it should be all explained by a fortuitous collision and only one collision? Mm-hmm. Why this could happen to explain all these properties? Mm-hmm. And in particular, I mean, we need an if true, is necessary an explanation, and even more with respect to other galaxies. I mean, it's so fortuitous.
Well, actually,
that everything is a collision, or otherwise there are more collisions, and we need to evaluate or to characterize more.
Yeah.
And the second point is, I think, the role of black holes here, in particular explaining the eccentricity of orbits or asymmetries, has been till now underdone in some sense. I mean, under-analyzed.
Yeah.
But of course, should need. I think that is an important point to see, is in my view. Thank you.
Okay, thank you for the questions. So I'll explain what, I'll answer what I thought the question was. So with respect to fortuitous event or fortuitous, well, kind of, the explanation is actually pretty simple, and these kind of events are ubiquitous in the simulations, right? So that's what I try to make the point, but very briefly. When you look in the zoom-ins, right, in, for example, in Auriga suite, right, you see that 1/3 of Milky Way like galaxies there undergone a similar head-on collision. So in that sense, it's a ubiquitous kind of interaction if you want, when you look at numerical counterparts of the Milky Way. So these happen all the time. And so it's not surprising then that that happened in the Milky Way, right? The other question was why we need one event rather than this comes simply from the mass conservation, right? So you can estimate the mass in this particular galaxy in stars that it brought in. And then you can, what we did separately, we measured the total mass of the stellar halo. So the total mass of the stellar halo is only twice, or maybe even less than that, higher than the total stellar mass or in the debris cloud left behind by that merger. So basically, there is not much room left for any other significant activity in the Milky Way. Why, right? So that's why it's the main event in the Milky Way. Why it's single? Because you could see in the alpha versus iron abundance track, the track is very coherent and it's one track rather than several tracks, right? So you need one system and it needs to be massive enough to self-pollute, self-enrich to this high metallicity, right? And it's one also system because all the stars are sitting on a single track in alpha versus iron abundance.
Okay, Christophe Pichon has raised his hand.
Hello, thank you again for a great talk. I guess I had two quick questions. One is sort of a follow-up. So in some sense, would you argue that it's surprising that if we look back in time, we do find one last major merger or significant merger in the history of the Milky Way?
Well, starting with Madao plot or something like this, I think I gave it away that I don't find it surprising that it's when you look back you find it. No, I don't find it surprising at all. And again, the fact that we found a large fraction of the Auriga zoom-ins have the same kind of event that also confirms that this is a typical behavior. My twist on it is different. We were looking for the evidence of this event and we didn't see it for a long time because we are sitting in the middle of this debris cloud and it's all around us and it's very difficult to notice when you are positioned right in the middle of this distribution, so that it eluded detection. But now once we've detected it, we can actually unpick what happened then. So,
okay.
Yeah.
And my second question, if I may, was you mentioned that after this event, you have like bulge, it corresponds to bulge formation, bar formation, thin and thick disk. So would you argue it's causal in the sense that some of these events have been triggered by this last merger, or would you argue that it's because things have become quieter so that these other processes can, I guess it depends which one,
yeah,
right?
Exactly. I think my view on this is pretty simple. It's a combination, right? It's things got quieter afterwards. And so transition from thick disk to thin disk, maybe to do with this. Some of what happened could be causality, right? So we do see, right, I mean, so obviously the splashing of the in situ, of the protodisk into the in situ halo is a causality, right? You produce this by the interaction. Bar seeding as well could be causality because again, we've looked at the some of the simulations and it does happen. Again, there could be many important numerical nuances whether you should be trusting it or not, but we do, it's easy to see the bar formation in this interaction. So it does happen. So it could be causal. Beyond that, it's very difficult to say. the bulge could be actually what we call a bulge, could be actually what I called here the splash and in situ halo, because the size of that component, I haven't had time to dwell on it, but the size of that component, right? If I show you how it looks like a puffed up bulge actually. So here's, right. So on the left, this is Auriga, right? And this is the red contours would be the old metal-rich stars on halo-like orbits. And it looks like a puffed up bulge, right? So what we see in the Milky Way, for example, with metal-rich RR Lyra, right, is a structure that is also of this size of order of, right? The slice through it is shown on the right-hand side. You see it's kind of 10 kiloparsec in extent, it's centrally concentrated, and it looks like a puffed up bulge. So it could be that a portion of the bulge was indeed created around that time. Whether there was a star formation episode like Gary implied, or whether there was just, you know, the kicking and splashing, or a combination of the two, I don't know yet.
Okay, thank you very much.
Okay, Joe, Silk.
Hi, Vasily. Thanks for a really inspiring talk.
Cheers.
Look, I'm very intrigued by one of the major problems in the dwarf galaxy area, and that is the vast plane of satellites. Now, in the case of the Milky Way, one recent paper pointed out that when you do a simulation of the history of our galaxy with the LMC in, then the probability of finding a vast plane of aligned satellites is increased significantly. So my question is, in your model now, where you're adding this past massive merger, would that have any impact in helping us understand the alignments?
So what we have not done, I understand the question, Joe, thanks very much. What we haven't done is that we have not actually quantified whether having this early merger helps to increase the probability of this perpendicular alignment of the satellites. We haven't done this. So when you say you're interested and concerned with this plane of satellite, is the fact of the orientation of the plane, or just the fact that the plane exists, or both? So what aspect?
It's that the plane exists and is so cold, basically. That's the issue.
Right.
And it may be that's related to its orientation, that is just a, you know, those two things are combined. It could be, well, dynamically combined, of course.
Yeah.
So I do have one related suggestion. Suppose your massive dwarf came in with a whole lot of smaller dwarfs.
Yeah.
Many of which survived. Could they, you know, the relic, could the vast plane be partly a relic of this, perhaps?
That I think we did look at, and I don't think that's probable because, well, at least in the simulations we've looked at, the big dwarf indeed came in with an entourage of smaller dwarfs, but they didn't contribute dramatically to the overall satellite population of the Milky Way. Maybe my view is kind of slightly different, is that this big dwarf was just the most massive lump of material that came in that accretion episode, or maybe it was, you know, the harbinger of things to come, right? The accretion started and there was matter being dumped on the Milky Way, and the largest chunk of matter was this big dwarf. But there were other things coming in, maybe also this other dwarf galaxy that eventually formed the plane of satellites. So I could see how this event was highlighting a particular change in the mode of accretion or direction of accretion. That I could see, right? And so I think that's where I would try to explore was it signifying the beginning of some a more prolonged accretion episode that could help create the plane of satellites? Maybe that's how I would see it. But its own satellites would not be responsible for creating the plane of satellites, right? And you can see, like, when you look at the LMC today, it does come with a satellites, but they're puny, right? So it has a bunch of ultrafaints, right? Okay, it has a lot of ultrafaints, but they're ultrafaints, right? There's nothing like classical dwarf satellites, right? So I suspect that something similar happened with that galaxy, although it's probably, yeah. So there could be some puny, smaller dwarfs, but not the classicals, yeah.
Okay, thanks.
Okay,
Yes.
and I see one more hand, David Valsgabo.
Yes, thank you, Vasily, for a wonderful talk.
Cheers. Thanks, David.
My question is related to the all-sky plot of the correlation coefficient in the latitude and longitude directions.
Yeah.
I noticed that there was a high correlation close to the galactic plane, which is not observed in the data. So what's the reason for that? So you see in the red and the blue, in the radial anisotropic model, it goes to +1, -1 very strongly towards the galactic plane.
There are multiple reasons for this, David. I think, well, the first one is that the radial anisotropic model is very simple, right? So we just take this two-humped radial velocity distribution, add the tangential components, and we sample from it, right? So this is not really a model of a merger or anything, right? It's a super simple, just to show that the overall large-scale pattern is very strong, and you can read it off by just looking, right? I think that I found that fascinating. But close to the disk plane, something interesting happened. We found a large number of RLIRA in the disk. And so close to the disk, you will start to dilute this radial. And of course, the RLIRA in the disk are doing what the disk stars are doing. They're rotating. So close to the disk, you'll start to dilute this highly radially anisotropic behavior with completely opposite mode of rotating, right? And so that was actually a bit of a striking, shocking discovery for me. I then realized that there is a history to this question, but I think what Gaia data has convincingly shown that not only there are thick disk RLIRA, but there are also thin disk RLIRA, right? And those are scarily quite young and all metal rich. And so they're completely different to what we think RLIRA are, but there are enough of them that they could start contributing close to the disk plane.
Oh, right, thank you. So related to Joe's question, I think the question is rather how the vast plane remains cold for, I mean, how come it could be that cold today, right? When we looked at that in M31, after less than 1 gigayear, the plane should have dissolved. And likewise, it should be the same. I mean, if the plane arises, say, 8 gigayears ago, it should be essentially dissolved by now, right?
But the dissolution of the plane question presumably is connected to the shape of the gravitational potential, right? So it depends on how this plane is oriented with respect to the dark matter halo, right? And so some planes can be much more resilient than others, depending on, I mean, you basically you have to invoke differential precession to disperse the satellites, right? It's phase mixing plus differential precession, right? And so, but that will depend on the orientation of the plane with respect to the shape of the halo. So one thing, it could be oriented in a fortuitous way that, you know, makes it more resilient against this differential precession spreading.
Right.
I mean, this is an interesting question because we're now starting to measure the dark matter halo shape in the Milky Way, right? And I think I would point you to the most recent paper led by Eugene Vasily, where we looked at the Sagittarius stream. And actually we get a pretty, well, first good constraint on the shape of the dark matter halo of the Milky Way. And it has an interesting and you know, non-trivial behavior as a function of radius. And so it would be interesting to compare what the planar groups like we observe in the Milky Way do if you put them into that dark matter halo. Do they stay or do they blur out?
Thanks, Vasily.
Cheers.
Okay, I see no other hand raised. Perhaps I have a short question to come back, Vasily, to the thick disk issue you mentioned many times. I know it's perhaps the answer is not simple. So you mentioned some kind of relationship between this last major merger, this event, and the thick disk. Now, my question is, the thick disk we see elsewhere also in other galaxies.
Yeah.
Do you think that such events have something to do with either the appearance or the end of the period of the thick disks? Should thick disks be related in such events or not at all? Or can you imagine to have thick disks in disk galaxies without such events?
Yeah, I think this is a question that I've been pondering for some time now. And I think the answer to it is maybe slightly unsatisfactory, but similar to the answer I gave to Christoph, is that it's there are multiple things happening, and some of it is causation and some of it is not. So I think the transition from this kind of turbulent thick disk to you know, colder thin disk probably happens naturally, right? However, we also see that you can splash out the pre-existing protodisk. If there was a disk-like thing before the merger, this will be splashed into a you know, even thicker component, right? So I think the nature of Milky Way's thick disk is it's multimodal, right? So there are different formation channels, right? And so the interaction, the splashing could have contributed something to the formation of thick disk. You could also, as we discussed today, promote star formation in the host, in the Milky Way, that would also contribute to the formation of the thick disk. And so I think parts of the thick disk are there because they are linked to that event and they were caused by it, but not all of the thick disk. And we've looked at this question in the paper with Rob Grant. So Rob and Daisuke Kawata on the paper. And so we did indeed see these multiple channels of formation of thick disk. So no, you don't need a merger to have thick disk and thin disk in a galaxy like Milky Way, but having a merger adds to it, right? So you have kind of this formation mechanism there too contributing.
Okay, thank you very much. Thank you very much for the nice talk. And,
and sorry, I didn't talk about black holes. I realized that was also part of the question that. Yes, sorry. It's a very interesting question that we haven't addressed much, and we started thinking about. And so the only thing that I can say is that that galaxy was the most massive galaxy that ever collided with the Milky Way. So if any dwarf galaxy is supposed to have a black hole and then deposit it into the Milky Way and let it wander, it's that galaxy, right? So chances are there was a black hole and it was deposited into the Milky Way. What is unclear to me, and that's what I'm trying to understand, is what actually happened to it, right? Because we see a strong radialization of the satellite of the progenitor, right? So it loses angular momentum in a very particular fashion. It radializes its orbit, right? And so the final bouts of disruption are on a highly eccentric orbit. And that's when the black hole is dropped into the Milky Way. It can come pretty close, right? As I showed, 2-3 kiloparsec away from the galactic center, but it would come on a highly eccentric orbit. To me, it's yet unclear what exactly is going to happen with the black hole on this highly eccentric orbit. Would it manage to merge with the Milky Way's one or not? Right. So that question is open, but I think it's a very exciting question because now this is the candidate for another black hole in the Milky Way.
I completely agree. I mean, it's real indication there and should be, the eccentricity is a signature in some sense, very and black holes are there. So thank you,
Yes.
Vasily.
Yeah, thank you very much. And thanks everybody for coming. I don't know if some people now wish to continue having some discussion with Vasily or just stop for lunch.
So I